Chapter 6, Applications of Integration, Section 6.1, Areas Between Curves. So we'll start off with a definition. If we want to get the area of the region bounded by the curves y equals f of x and y equals g of x, and the lines x equals a, x equals b, where f and g are continuous, and notice f is bigger than g, for all x in the interval, then we say that the area between these two curves, or bounded by the two curves, is the limit of the Riemann sum of the difference of the two functions, which we know by definition is the integral of the difference between the two functions. So what we basically do is we draw a rectangle to get the height between the two functions, and we see that a rectangle underneath f would have a height of the y value there, which is the f value, and then underneath that, this rectangle has a height of minus g, because this area would be negative signed area. So if we want to make it positive, we just take minus. If we were looking at this end, and we wanted to know the height of this rectangle, then we could get a rectangle underneath f, and we could cut out a rectangle underneath g. We can cut out this bit. And then if we take that minus that, then we get the rectangle that we want, which is exactly what this means by subtracting. So let's do an example of that. Let's find the area of the region bounded above by y equals e to the x, bounded below by y equals x, and bounded on the sides by x equals 0 and x equals 1. First, we draw what's going on. So here's y equals x, y equals e to the x roughly, and then we need a straight line through the origin for y equals x. So that's roughly what that is. And then here's x equals 1. And here's 1, 0. Our top equation is y equals e to the x. And our bottom one is y equals x. So it looks like a rectangle if we draw it. Will have a height equal to e to the x minus x, because it'll be the difference in the two y values. The width is a tiny little delta x, tiny little change in x. Assuming that we take the limit of this Riemann sum, then we are just drawing tons and tons of rectangles as their widths get smaller and smaller and smaller. So in this case, our top function is f of x equals e to the x. Our bottom function is g of x equals x. We're going from a equals 0 to b equals 1. So our area becomes the integral from 0 to 1 of the difference of our top function and our bottom function. So we take e to the x minus x dx, and we integrate. The antiderivative of e to the x is just e to the x. The antiderivative of x is x squared over 2, so we'll subtract half x squared. And then we evaluate that from 0 to 1. We end up with e minus a half minus 1, which is just e minus 1.5. Oops. Let's do another example. Let's find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Okay, let's see if I can draw a parabola. It's one parabola. And another one. So y equals x squared is the happy face one that opens up. So that's this top one. Actually, let me do another color. How about I grab see how this one looks. Let's do green for this one. Okay, so pretty bad looking parabola, but maybe it looks a little bit clear which one's which now. This frowny face parabola is y equals 2x minus x squared. And it's on the top, notice, for our region, because this is the region we're going to want. So I'll write yt for top. Then our other parabola is our happy face one, which is y equals x squared. But this one is actually on the bottom, so I'll write yb for bottom. Notice if you had looked over here, then it looks like it's on the top, or if you look over here, it looks like it's on the top. But we don't care about the regions. We only care about the region enclosed by the parabolas, which is this region over here. And in that region over there, they switch, and the green one gets on top and the blue one gets in the bottom. So as far as our integral goes, that's all we're going to care about. However, we have one other issue for this problem. They didn't give us the a or b values. So we need to figure out what this point is and this point is to know how far we have to integrate. So this looks like it's 0, 0. But the other one, we probably have to actually do a little more work for. So let's see where they intersect. That is, let's see where x squared is equal to 2x minus x squared. That'll be when the two y values are equal. So solving that, we get 0 equals 2x squared minus 2x. We can factor out the 2x and get x minus 1 on the inside. So that implies that x equals 0 or x equals 1. So like we saw, 0, 0 is going to be a point, but the other one is going to be 1, 1. So that means this point is 1, 1. If we draw a little rectangle, let's see if I can actually draw this thing. I guess not. Maybe something like that. Yeah, roughly. So let's say this is a tiny little rectangle. It has a width delta x. Then, yeah, it looks like the height of this rectangle should be the area underneath the y value under for yt, the top function, 2x minus x squared. And it looks like we just have to cut out this area underneath, which is the area underneath the function y equals x squared. So we should be able to get the area by doing the integral of our top function minus our bottom function, which we plug in, and we get that it's the integral of 2x minus x squared minus x squared, which is the integral from 0 to 1 of 2x minus 2x squared. And we can pull out our 2 and get this is x minus x squared dx. So that's 2 times the antiderivative, which is x squared over 2 minus x cubed over 3, evaluated from 0 to 1, which is 2 times a half minus a third, which is 1/3. So notice when you do these problems, you have to be very careful of which function is going to be on top or bottom. You might assume, oh, y equals x squared, that's a nice happy parabola, minus x squared, that should definitely be below it. But it turns out the region enclosed by these two guys actually is the reverse of what you might expect. Let's find the approximate area of the region bounded by the curves y equals x over square root x squared plus 1 and y equals x to the fourth minus x. Notice in this case, if you take x over square root x squared plus 1 and set it equal to x to the fourth minus x in order to try to find the endpoints, which again they didn't give us, then that looks really challenging to solve. And in fact, it's actually impossible to solve exactly. So why don't we get our handy dandy calculator emulator out. We'll go to y equals, we'll put in x divided by square root of x squared plus 1, and we'll put in x to the 4th minus x. Oops, x. Always doing that. There we go. And we'll graph it. Okay, doesn't look too bad, but let's zoom in a little bit. Alright, nice. It looks like they intersected 0, 0. And at some other point over there, let's see what that point is. Second trace to get to the calc. Let's get 5 for intersection. Our first curve is going to be that. Second curve is red, and then we'll move over to that other point. It looks like the x value is about 1.18. So let's grab that. Goodbye, calculator. Calculator. So assuming that x is about 1.18 at that point of intersection, that makes our endpoints from 0 to 1.18. So that means that our area should be approximately the integral from 0 to 1.18 of our top function, which was the blue one. That was the one I typed in first, which was this one, minus our bottom function, which is our red one, which is this guy. So that means it'll be x over square root x squared plus 1 minus x to the 4th minus x dx. We have a bit of an issue here. This looks easy to integrate with the reverse power rule, but my other half of the integral looks a little bit challenging. So how about we take a break and let u equal x squared plus 1. That means du will be the derivative 2x dx. We have another issue though. We've got limits over here that we have to substitute in. So if x is 1.18, then 1.18 squared plus 1 gives us a u value of approximately 2.39. If x is 0, that's just 0 squared plus 1, so then u is just 1. By doing the substitution, I can replace the x and the dx. This will just be square root u, so that makes things a lot easier. So that means my area will now actually be approximately equal to half of 1 to the integral from 1 to 2.39 of du over rad u. And then I won't mess with this part because it's perfectly fine. So I'll just leave that as the integral from 0 to 1.18 of x to the 4th minus x dx. So when we take our antiderivative, we get square root of u, because this is u to the minus 1/2, so increasing it by 1 gives you u to the half, which is square root of u. And then that will also cancel out our half. And for our other integral, we get x to the 5th over 5 minus x squared over 2, evaluated from 0 to 1.18, which is equal to square root 2.39 minus 1 minus 1.18 to the 5th over 5 plus 1.18 squared over 2, which is about 0.785. The figure shows the velocity curves for two cars, A and B, that start side by side and move along the same road. What does the area between the curves represent? use the midpoint rule to estimate it. Well, the area underneath this curve A is the distance traveled from whatever interval I'm at. So in this case, 0 to 16. Similarly, the area underneath B is the distance traveled from with the car B from 0 to 16. So that means that the area between these curves will represent the distance between the cars after 16 seconds. So the area between the curves is the distance between the cars after 16 seconds. Let's now use the midpoint rule to estimate our distance between the cars after 16 seconds. Notice that time is in seconds, velocity is in miles per hour. Again, we want to convert miles per hour to match up with seconds. When we convert hours to seconds, we'll get velocity values way too small, so let's convert velocity to feet per second. So we'll have time, we'll make a table, velocity of car A, velocity of car B, and while we're here, let's get the velocity of the difference, because that's what we'll have to integrate. So at time 0, the velocity of A was 0, velocity of B is 0, so when we subtract, we get 0. At time 2, the velocity of A is 34 about, velocity of B is about 21. When we subtract, we get a difference of 13, and so on. Remember that we did this so that we could convert our units. So all of these are now in feet per second. If we want to use the midpoint rule, we need to choose a number of subintervals. So if we're going from 0 to 16, how we break that into 4 chunks. So we can choose n equals 4. So that means that our first interval goes from 0 to 4, the second one goes from 4 to 8, 8 to 12, 12 to 16. So our difference is delta t, which is 4. That's the width of each of our subintervals, so that's be the width of each of our rectangles for this sum that we're going to use to approximate. We're using the midpoint rule, so we need to find a bunch of sample points that are all midpoints. So for our first one, that's 0 to 4, the midpoint would be 2. Second one, 6 to 8, the midpoint would be 6, and so on. So we write that t1 bar is equal to 2, t2 bar is equal to 6, t3 bar is equal to 10, and t4 bar is equal to 14. Our integral therefore becomes the integral from 0 to 16 of the difference in our two velocities, velocity A, our top one, minus velocity B, our bottom one. We approximate that using the midpoint rule, so we have delta t times our function evaluated at these midpoints. So that means we look at this one over here at 2, so that's 13. Then we look at t2 bar at 6, so we look at 23. And then we look at 28, and then 29. Because those are all our difference values. Okay, we work that out and we get that this is 4 times 93, which is 372 feet. The figure is an example of a pathogenesis curve for a measles infection. It shows how the disease develops in an individual with no immunity after the measles virus spreads to the bloodstream from the respiratory tract. The patient becomes infectious to others once the concentration of infected cells becomes great enough, and he or she remains infectious until the immune system manages to prevent further transmission. However, Symptoms don't develop until the amount of infection reaches a particular threshold. The amount of infection needed to develop symptoms depends on both the concentration of infected cells and time, and corresponds to the area under the pathogenesis curve until symptoms appear. The pathogenesis curve in the figure has been modeled by f of t equals minus t times t minus 21 times t plus 1. If infectiousness begins on day t1 equals 10 and ends on day t2 equals 18, what are the corresponding concentration levels of infected cells? So that means that we want the value of this function, f of t1 and t2. So that means we want f of 10, which is negative 10 times 10 minus 21 times 10 plus 1, which is 1210 cells per milliliter. Similarly, we want f of 18, so that's negative 18 times 18 minus 21 times 18 plus 1, which is 1026 cells per milliliter. And that's over here. So that's these two values, from when infectiousness begins to when infectiousness ends. The level of infectiousness for an infected person is the area between n equals f of t and the line through the points p1 and p2 at t1 and t2, measured in cells per milliliter days. Compute the level of infectiousness for this particular patient. So we need to go back. This point that we just got is P1, because that's at T1, and then this point over here is P2. We want the area between this line that goes through these 2 points and the curve. So we want this area. And we can get that by subtracting. We'll take our top curve, the curve that we were given, that orange curve, which is modeled by f of t equals n, and we will subtract off the equation for this line and then integrate. So to get the equation of the line, we need to get the slope of the line. So let's do that. So the slope is m equal to the difference in the y values we computed was 1026 minus 1210 over 18 minus 10, y2 minus y1 over x2 minus x1. So that's negative 184 over 8, which is negative 23. Therefore, the equation of our line, we can do y minus y1 equals m times x minus x1 to write this thing in point slope form. We can pick one of the points. How about 1210, where t was equal to 10, so that we get n minus 1210 equals our slope, negative 23, times t minus 10. And we get that n is equal to negative 23t plus 1440. Our integral, therefore, becomes the integral from 10 to 18 of our top function, f of t, minus our bottom function, the line that we just built, minus 23t plus 1440. And we plug in now for f of t. So we get minus t cubed plus 20 t squared plus 21t plus 23t minus 1440. We just expand the function they gave us for f of t. And then we keep on simplifying. We get minus t cubed plus 20t squared plus 44t minus 1440 dt. We can now take our antiderivatives. we get minus t to the 4th over 4 plus 20 t cubed over 3 plus 44 t squared over 2 minus 1440 t from 10 to 18. So that equals negative 6156 minus 8033 and 1/3, which is about 1877 cells per milliliter days. The area between the curves y equals f of x and y equals g of x, and between x equals a and x equals b, is the integral of the absolute value of the difference between those two functions. You might be saying, hey, you already just told me that the area between the curves was just the difference. Where are you getting this absolute value from? Well, that was making an extra assumption that f was bigger than g. In this case, there are no assumptions regarding these two functions. One could be bigger than the other. One could, rise above and below and flip-flop. Doesn't matter. As long as you take the absolute value, that forces your difference to always be positive, so you're always considering a positive area, and then you don't have to worry about which one is on top and which one is the bottom. Let's do an example by finding the area of the region bounded by the curves sine and cosine from 0 to pi over 2. Okay, can I draw cosine? Maybe. Let's see if I can now switch colors and draw sine. Oh, actually, let me label this first. This is y equals cosine x. Maybe. Depends whether you have good eyesight. And then maybe this will be y equals sine. Nope, it won't be. Try again. I want to get a little bit higher. I'm trying to make it look as symmetrical as possible. Okay, I think that'll do. So that's y equals sine x. And we want the area, well, from 0 to pi over 2. Notice that cosine is 0 at pi over 2. So this is pi over 2. So we want this area. It's almost symmetrical if you close your eyes. So that means it's the area of this part plus the area of this part. These are the two areas that we want. And we need to figure out where this intersection point is over here, because that intersection point will tell us how we can split our absolute value function. Remember, absolute value is a piecewise function. In this case, we can write it as cosine on top and sine on the bottom for a1. But then the absolute value would be negative if we just kept doing that for a2. For a2, in order to make the difference positive and keep absolute value, we're going to have to switch and make sine positive. So we need to know where we have to make this switch happen. So let's set sine equal to cosine. Well, that happens from 0 to pi over 2 when x is pi over 4. That's when they're both rad 2 over 2 or 1 over rad 2. We don't have to consider other values where they're equal because we're stopping at pi over 2. So now we know that this is pi over 4. Now, this is the line x equals 0 on the left and x equals pi over 2 on the right. So now we have the complete picture for our bounded region. Writing our total area as the integral from 0 to pi over 2 of the absolute value of cosine minus sine. Well, that's going to be equal to a1 plus a2. So let's write those as two separate integrals. We'll go from 0 to pi over 4, and then we'll go cosine x minus sine x, because that'll make it the difference positive because cosine's on top and sine is on the bottom from 0 to pi over 4. And then we'll add that to the integral from pi over 4 to pi over 2, where notice over here we have to write sine on the top and cosine on the bottom. So we'll put sine first when we do our subtraction to make sure that this is positive. Now we do our integral. So when we take the antiderivative of cosine, we get sine. For sine, we get minus cosine, so the minus cancels. And then we do another set of antiderivatives. We get minus cosine minus sine. And you should always test these and make sure that when you take the derivatives, you get back to the integrand that you wanted. Evaluating these from 0 to pi over 4 and pi over 4 to pi over 2, we get 1 over rad 2 plus 1 over rad 2, which we already said is when sine and cosine are equal. And we subtract off 0 and 1. To be kind of careful, because in this case there is a contribution, but only for cosine. When you take sine as 0, it disappears, but you have to be careful if cosine is 0. Similarly, we get minus 0, minus 1, plus 1 over rad 2, plus 1 over rad 2. Notice this value is the same as this one, so these two integrals were actually equal. So these two areas were actually equal. So by noticing the symmetry over here to begin with, we could have saved time and done half as much work. So we'll have to just be more careful in the future. This ends up being 2 rad 2 minus 2. Some regions are best treated by regarding x as a function of y. If a region is bounded by curves with equations x equals f of y and x equals g of y equals c, and y equals d, where f and g are continuous and f of y is greater than or equal to g of y, then its area is this, the difference in the two functions of y. So in this case, we're looking at horizontal rectangles that we stack up. Each horizontal rectangle has a tiny change in height of delta y. So this can be a little bit confusing because you have to switch to x equals functions instead of y equals functions. In this case, you always want to look at the right function minus the left function, because this is the more positive function because x values go up from left to right. So let's draw one and do an example. If we want to find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6, that's the same thing as drawing the parabola x equals half y squared minus 3. So let's draw that. Nice x equals parabola. And then we can draw our line y equals x minus 1. Looks something like that. So, oh yeah, I forgot. Switch color. Let's make that green. Okay, good. So this line, which is our right function, I'll write it as xr, is equal to y plus 1. That's this one. You just add 1 to get x by itself. Then my left function, xl, is equal to half y squared minus 3. So I need to figure out what these points of intersection are, and then I can figure out what the area will be. Notice that if we draw a rectangle over here horizontally, then the rectangle has a tiny change in height, delta y. So let's figure out where these things intersect. We'll have to solve the system of these two equations. So that's y squared equal to 2 times y plus 1 plus 6. All I do is replace x with what x equals, which is y plus 1 when you add 1 to both sides. So then I get y squared minus 2y plus, minus 8 equals 0. So that means y plus 2 times y minus 4 equals 0 when we factor. That implies that y is equal to minus 2 or 4, which means if we go back in and figure out what x is, we plug in minus 2, we add 1, we get that x is minus 1 at minus 2, and we get that x is 5 at 4. So now we have our points of intersection, so now we know our limits. You have to be a little bit careful. In this case, we have a tiny change in y delta y. So we're integrating with respect to y, so we're going from bottom to top, we're not going left, right. So that means that we're going from these two y values over here. At minus 1, minus 2, we're only considering the minus 2. And over here at 5, 4, we're only considering the 4. We didn't really even have to plug in to figure out that this was minus 1 and 5. So we're going from the bottom at minus 2 to the top at 4. We'll take our right function, xr, and subtract our left function, xl. And this will give us our area between these two curves. So that ends up as the integral from minus 2 to 4 of our right function, y plus 1, that's the green one, minus our left function, which is the parabola, half y squared minus 3. So we simplify and we get our integral of minus half y squared plus y plus 4. And then we keep evaluating. We'll take our antiderivatives at this point and get y cubed over 3. And we get y squared over 2. And we get 4y. All evaluated from minus 2 to 4. So that ends up becoming minus 1/6 times 64 plus 8 plus 16 minus 4/3 plus 2 minus 8, which is 18. This is technically not the only way you could have solved this problem. If you really hate integrating with respect to y, you could have integrated with respect to x. You just have to draw your region a little bit differently. So you would have drawn it something like this. See if I can get this parabola. And then I'll draw this thing. Still intersects at 5, 4, and then this intersects over here still at minus 1, minus 2. This value where we hit the x-axis is at minus 3 for x. Here's our curve. We have to be very careful over here though. If we want to write this as a function of x, we can't write y squared. So we have to write this as a top curve. So this could be our top curve, y equals square root 2x plus 6. And then our bottom curve becomes y equals minus square root of 2x plus 6. So how about I use another color for that? This curve over here becomes y equals minus square root of 2x plus 6. So then this curve, this green curve, is still y equals x minus 1. So now we have to see which one's on top and which one's the bottom. But notice it switches a little bit. If I go from -3 and I walk over all the way to -1, then I'm looking from here to here. And in this case, my bottom curve is purple and my top one is blue. But then as I keep walking from left to right, I notice that the purple curve becomes completely irrelevant and the green curve comes into play. And now the top curve is still blue, but the bottom one is no longer purple and now it's green. So if I really want to write this as an integral with respect to x, I have to write it as this area plus this area. So I would have to write it as, let's totally separate this. I'd have to write it as a1 plus a2, where we would have to write it as the integral from -3 to -1 of square root of 2x plus 6 minus the square root of 2x plus 6. So that means they cancel and become positive. That's respect to x. That's my first one, a1. So that's from here to here, where blue is top and purple is on the bottom. But then from -1 on to 5, I would have to switch, still have the blue one on top, but now on the bottom I've got the green one, x minus 1. And evaluating these two integrals is so much more work than just evaluating this integral over here. So you really should get comfortable with integrating with respect to y, because for some problems it's way easier if you can write functions, x equals functions of y rather than y equals functions of x for everything.